Well, welcome back. We're now working in section 5.2, and 5.2 is congruence class arithmetic, really looking at that ring structure for f adjoint x modded out by p of x and those equivalence classes. But we have to define how to add and how to multiply to be able to create that ring structure. We got the elements off those equivalence classes because whatever p of x is, when you divide by p of x, the equivalence classes are the remainder polynomials, and it's always degree 1 less than what degree of p of x that you're modding out by. So, Theorem 5.6 defines this addition and subtraction. It says, let f be a field, and p of x a non-zero polynomial in f adjoint x. If congruence class f is equal to congruence class g, and congruence class h is equal to congruence class k, and f adjoint x modded out by p of x, this congruence class world, then congruence class f of x plus h of x is actually equal to congruence class f of x plus congruence class h of x. And number 2, congruence class of f of x times h of x is actually equal to congruence class of f of x times congruence class of k of x. So this is how you add and how you multiply equivalence classes. You literally just add the polynomials together and multiply the polynomials. But remember, if you get bigger than the degree of p of x, the degree or bigger of p of x, you're going to have to divide by p of x and knock it back down into a degree less than p of x polynomial. Remember, it's the remainders when you divide by p of x. Sometimes these guys don't get bigger than p of x, but when they get the same size or bigger, you got to divide by p of x to see what it's equivalent to. So definition, let f be a field, and p of x a non-constant polynomial in f adjoint x. So notice we went from non-zero to non-constant polynomial. You want at least a x out of it. You want this thing to be more than just a constant polynomial, because that's not very exciting. So now you want them to be a non-constant, so at least degree 1 or better. Addition and multiplication f adjoint x modded out by p of x is defined by, and just as we saw, equivalence class f plus equivalence class g is going to be equal to that equivalence class of f of x plus g of x. Equivalence class f of x times equivalence class g of x is equal to equivalence class f of x times g of x. This is how you add in f adjoint x modded out by p of x. You just add the two equivalence classes together. And this is how you multiply. You just multiply the two equivalence classes together. Which means that if these guys get too big, greater than or equal to the degree of what p of x is, then you've got to take the resultant and divide by p of x and see what the remainder is and get that. It's going to be the same equivalence class. It's always the remainder. So, with this addition and this multiplication, f adjoint x modded out by p of x is a ring. And so what we're going to be focusing on in chapter 5 is 1, the ring structure, and 2, what kind of ring is it going to be. So catch a pattern of what we did now and what we did way back when in chapter 2. So here we go. I got a problem for us to work together on this one instead of me just reading off the ideas and then kind of paraphrasing behind them and stuff. So here is an example. I have z2 adjoint x modded out by x squared plus x plus 1 polynomial. All right. z2. If I'm going to make myself an example, I'm going to do something nice. Remember, you got to have a field adjoint x. So to get a field in the world of z modulo n has to be prime. 2 is prime. But with z2, I just want to remind you, z2 is the element 0 and 1. Pretty much the binary concept here. Equivalence class 0 and equivalence class 1. All you get is zeros and ones. So look at this polynomial. X squared plus x plus 1. X squared plus x plus 1. The coefficients are 1, 1, and 1. They either have to be ones or zeros. But what are we dividing by? X squared plus x plus 1. The degree is 2. So the equivalence class has to be a degree less, 1 less than degree 2, which means it's a degree 1. And a degree 1 polynomial is what we call linear. Linear is going to look like ax plus b, where a and b are elements of the field z2. So, here we go. Let's write them all down. First off, how many of these guys do we have? 0 and 1. We got two options for A. 0 and 1. We got two options for B. 2 times 2. There are 4 equivalence classes. The 4 equivalence classes are, let's make A equal to 0 and let's run the gamut on B. B could be 0, so you get the 0 equivalence class. B could be 1, you get the 1 equivalence class. A could be 1, that would be 1x. And B would be 0. And then the last one, A could be 1 and B could be 1. 1 and 1, that would be x plus 1. 1, 2, 3, 4. Got them all. We're talking about ring structure here. So let's create rings, and let's talk about what these rings are going to be. So I'm going to go back to the old elementary school and write out my addition and multiplication tables for these equivalence class elements of Z2 adjoined x modded out by x squared plus x plus 1. So my equivalence classes are 0, 1, x, and x plus 1. And on the column, 0, 1, x, and x plus 1. Well, this is addition, so this is not going to be overly difficult for us. What's the 0 equivalence class plus any other equivalence class? Remember how we define how to add equivalence classes. You just add them and put an equivalence class here, and it's got to be one of these elements, though. So 0 plus 0 is 0, 0 plus 1 is 1, 0 plus x is x, and 0 plus x plus 1 is x plus 1. 1 plus 0 is 1. 1 plus 1 is 2, but 2 is equivalent to, and Z2 is back to 0 again. 1 plus x is, pretty much 1 plus x. And 1 plus x plus 1 is x plus 2, but 2 is equivalent to 0, so you get x back again. X plus 0 is x. X plus 1 is, pretty much x plus 1. X plus x is officially 2x, but 2 is equivalent to 0. So it'd be 0 times x, which is just 0. X plus x plus 1 is 2x plus 1, but 2 is equivalent to 0, so it'd be 0x plus 1, which makes it just 1. X plus 1 plus 0 is x plus 1. X plus 1 plus 1 is x plus 2, but 2 is equivalent to 0, so you're back to x again. X plus 1 plus x is 2x plus 1, which is just 1. X plus 1 plus x plus 1, that'll be 2x plus 2, but 2 is equivalent to 0. 0 times x plus 0 is 0 equivalence class. This is your addition table for the ring Z2 adjoint x modded out by x squared plus x plus 1. Now, that wasn't too difficult because when you got 2, 2 is equivalent to 0 in Z mod 2. What about the multiplication table? That's going to be a little more interesting. So here we go. The equivalence classes once again are 0, 1, x, and x plus 1. 0, 1, x, x plus 1. Now we're multiplying. So 0 times any equivalence class is 0. 0 times 0 is 0. 0 times 1 is 0. 0 times x is 0. 0 times x plus 1 is still 0. 1 times 0 is 1. 1 times 1 is 1. Excuse me, 1 times 0 is 0. Get that right. Jump the gun there. 1 times 1 is 1. That's much better. 1 times x is x. And 1 times x plus 1 is x plus 1. X times 0 is 0. X times 1 is x. Here we go. X times x is x squared. But x squared is outside my range. So who is x squared going to be equivalent to? Well, time for long division. I'm going to take x squared plus 0x plus 0. That's my dividend. My divisor is the x squared plus x plus 1 because that's what we're modding out by. In the Z2 adjoint x modded out by x squared plus x plus 1. So you're going to divide by x squared plus x plus 1. And we're going to do long division. What times x squared is x squared? It's 1. So multiply. That'll be x squared plus x plus 1. You're going to subtract. That cancels. Change all your signs. So 0x minus x is minus x. Plus 0 minus 1 is minus 1. X squared plus x plus 1 doesn't go into negative x, but you remember you got to put it back in terms of that Z2 adjoint x. Z2's got to be either 0 or 1, so negative 1, just pretty much add 2 to it, would become positive x. and negative 1 adding 2 to it becomes positive 1. You've got to convert these coefficients back into Z2, and the easiest way is just keep adding 2 until you get a number between 0 and 2, not including 2. So x squared is equivalent to the equivalence class x plus 1. Now, what is x times x plus 1? That would give you equivalence class of x squared plus x. But again, to figure out who this guy is, because he's not one of my elements, I got to boom him back down. I'm going to divide by x squared plus x plus 1 into that dividend of x squared plus x, officially plus 0. There's my dividend there. Now, what times x squared is 1 again, so that'd be x squared plus x plus 1. Subtract changes your signs. This cancels and this cancels. 0 minus 1 is negative 1, but I got to put it back in terms of that z2 adjoint x, which makes it positive 1. So that's the equivalence class 1. Now, last one, x plus 1 times 0 is still 0. X plus 1 times x is going to be, x plus 1 times 1 is going to be x plus 1. And x plus 1 times x is going to be x squared plus x, but x squared plus x is going to be 1. And x plus 1 times x plus 1 is x squared. Oh, we got to do that one. X squared plus 1 times x squared plus 1 is going to be x squared plus 2x plus 1. I folded out in my head. But 2 is equivalent to 0, so that's x squared plus 1. And I'm going to take that x squared plus 0x plus 1 and divide it by the x squared plus x plus 1. And it goes x squared plus x plus 1 goes x squared plus 0x plus 1 one time. You multiply, distribute x squared plus x plus 1. Subtract changes your signs. This cancels, you get negative x, and that cancels too, so you get negative x. But you got to get that thing back in z2 adjoint x, so take that coefficient of negative 1 and add 2 to it, and you get positive 1, so it becomes 1x, which is equal to just x. And there is my multiplication table. And it forms a ring. So the next question, of course, is what kind of ring is it? This is the multiplication table and addition table for z2 adjoined x modded out by x squared plus x plus 1. What kind of ring is it? Well, to know what kind of ring, because it is definitely a ring. Okay, so once you get the ring, does it commute? So you really focus on the multiplication tables. So if it commutes, you got your diagonal and the upper triangle and the lower triangle parts end up matching up each other. So 1 times x is the same thing as x times 1. So, you know, around the diagonal, everything must match up, which it does. So it's a commutative ring. Has a ring with identity because you multiply by 1, you get the every other element back again. So it's a commutative ring with identity. Is it an integral domain? Is it a field? What do we got here? Well, since I don't have any zero divisors, this thing is definitely going to be an integral domain. I don't have anybody, a non-zero element times another non-zero element give me 0 down here, so it's definitely an integral domain, but is it a field? All non-zero elements, which is just the 3 elements, 1, x, and x plus 1, should have a multiplicative inverse. 1 times 1 is 1, yeah, that works. X times x plus 1 is 1. And x plus 1 times x is 1, so every non-zero element has a multiplicative inverse. This guy actually is a field. That's why you got to know your definitions. Now, in terms of this, some theoretical questions we have thrown at you. Theorem 5.8 says this: let f be a field, and p of x a non-constant polynomial, and f adjoined x. Then the ring f adjoined x modded out by p of x, a commutative ring with identity that contains f. You're always going to get a commutative ring with identity because f adjoined x commutes, so these modular classes will also commute. And they also contain f. Let me show you the idea of containing f. This f in this problem was z2. So if you look at your equivalence classes, z2 is 0 and 1, and there they are right there. It contains f. There's 0 and 1. There's the z2 part and a few other elements added onto it. That's what this theorem is referring to. Theorem 5.9 says this. Let f be a field, and p of x a non-constant polynomial in f adjoint x. If f of x, an element of big F adjoint x, if f of x is an element of big F adjoint x, and f of x is relatively prime to p of x. Remember, relatively prime means that the GCD of f of x and g of x is actually equal to 1 in that f world, whatever that f world field happens to be. Then the equivalence class of f of x is going to be a unit in f of x join mod p of x. A unit is a multiplicative invertible element. Again, as we refer back to this guy, everybody in this problem had a GCD relative to x squared plus x plus 1 was 1. The non-zero guys, of course, because every one of them has a multiplicative inverse. Only guys that are relatively prime to what you're modding out by will actually be units. But 1, x, and x plus 1 are all units because they have a multiplicative inverse. So that's what this theorem is telling you. So if you got a bunch of zero divisors and whatever within your ring, oh, don't worry, you could still have some possible units. But the units are going to be, you look at the GCD of f of x, and it's relatively prime to, and there should be a p of x there. I don't know where that came from. F of x and p of x, the guy you're modding out by. F of x and p of x, if that has they're relatively prime to each other, then the equivalence class of f of x is going to be a unit in f adjoint x modded out by p of x. If you're relatively prime to what you're modding out by, you're going to be a unit. So, an example here. I've got q adjoint x modded out by x squared minus 2. Now, since you're modding out by x squared minus 2, degree of this guy is 2, so when you divide by x squared, you're going to get a remainder of linear terms, ax plus b. It's always degree 1 less, so it's ax plus b, where a and b are got to come from the field, the rationals, which means you got an infinite choice of rationals for a and infinite choice of rationals for b. So you got an infinite number of congruence classes in this problem. So the last one we did was a finite congruence class. This one's infinite. But that doesn't matter. Notice something or other. Since this, notice, and I just came up with this one just to help you out because we're in q adjoint x. When I take the equivalence class of 2x plus 5 and multiply it by negative 2/17 x plus 5/17 and add that to x squared minus 2 times 4/17, I actually get 1. You don't have to trust me on this one. I stole it out of the book. But if you FOIL this thing out and distribute the 4/17 and combine like terms, everybody cancels, but you got left with a constant 1 left over. So, noticing that, and then you start playing in the world of congruence classes. And this is how you do. You just put a big old bracket around everybody. Now everybody's a congruence class. But congruence classes have a wonderful property here. So everybody's a congruence class, but when you break it up, remember how to add congruence classes, you just add each part so you can break up that congruence class. So it'll be the congruence class of this guy plus the congruence class of this guy equals the congruence class of 1. And with multiplication, you can take the congruence class of each one of these guys, and that's what I did here. So your congruence class of 2x plus 5 times the congruence class of negative 2/17 x plus 5/17 plus congruence class of x squared plus 2 times the congruence class of 4/17 equals the congruence class of 1. But since you're modding out by x squared plus minus 2, that congruence class would be equivalent to 0. It's kind of like in Z7, 7 is actually the 0 congruence class. And if that's going to be 0, then you're left with, this part will go away, you're left with congruence class 2x plus 5 times congruence class negative 2/17 x plus 5/17 equals 1, which means these two guys are inverses of one another. So this negative 2/17 x plus 5/17 is the inverse of the multiplicative inverse. Both of them are units, but it's the multiplicative inverse of 2x plus 5 in q adjoint x modded out by x squared minus 2. So here's some other ones. Again, just trying to get you a feel for what this stuff looks like here in section 5.2. So let's do this problem here. So I created some problems for you guys. So there's two ways I'm going to ask you, because it depends on the size. I'm going to give you congruence class. This first one is Z5 adjoint X modded out by 4X cubed plus X plus 2. So Z5, 5's prime, so Z5 is a field, adjoint X. Remember in Z5, you're allowed to have only 0, 1, 2, 3, 4. You look at my coefficients. I got 4, I got a 1, and I got a 2. So all my coefficients come from Z5. So I got Z5 adjoint X modded out by 4X cubed plus X plus 2. What would the style of the congruence classes look like for this Z5 adjoined X modded out by X squared, 4X cubed plus X plus 2? Well, since you're dividing by or modding out by an X cube, the remainders, that's the key. When you divide by an X cube, you get an X squared, the biggest remainder possible. So this will be a quadratic. AX squared plus BX plus C, where A, B, and C are elements of Z5. So the question is, because that's a lot of them, how many congruence classes are there? Well, for Z5, just to remind you, Z5 is 0, 1, 2, 3, and 4. But there are 5 congruence classes. So I've got 5 choices for A, I got 5 choices for B, and I got 5 choices for C. And this is called the multiplication principle when you're actually trying to figure out the number of possible ways something can happen. This idea of permutations and stuff called the multiplication principle. So 5 choices of A times 5 choices of B times 5 choices for C, that's equal to 125 congruence classes. This will be a ring with 125 elements in it, is what this guy's going to be. You begin to see these stuff really blowing up on you guys and stuff. But remember, you know, are these guys going to be isomorphic to other rings? Probably, possibly, could be. But also look at it from a code theory perspective in terms of being able to follow this stuff around. If you know what's going on, it's easy. If you don't know what's going on, that's where you need your hackers and code breakers to try to figure this stuff out. So Z5 adjoined X modded out by 4X cubed plus X plus 2 actually has 125 equivalence classes. This is a little better. I've got Z2 adjoined X modded out by X squared plus X plus 1. Okay? And Z2 adjoined X, when you mod out by X squared plus X plus 1, gives you that AX plus B look, because that's a degree 2, where A, B come from Z2. And so then Z2, just remind you, is the binary equivalence class, zeros and ones. So your elements are 0, 1, X, and X plus 1. And what kind of ring was it? Well, this is the guy that we did before. So if we go back over there and take a look at it, here he is right here. But you had to look under the multiplication table to see that there are no zero divisors, so it's an integral domain, and zero divisors are non-zero elements multiplied by non-zero elements to see if I'm going to get 0, but I don't get any 0, so no zero divisors means integral domain. But then let's see if it's even stronger than that. Are all non-zero elements units? Every guy has a multiplicative inverse, so this guy is actually a field. But I had to look at the multiplication table for right now. There's going to be other ways down the road. So, and that's what we're going to be focusing on in section 5.3. We're going to be looking at this special polynomial p of x that we're modding out by and some of the properties thereof, and help us to define what kind of rings we get. Because this wasn't too bad, because I could do the multiplication table for Z2 adjoined X modded out by X squared plus X plus 1. But look at this guy here. I have 125 equivalence classes. I don't want to draw that out and look at the multiplication tables and try to figure out what kind of ring it is. There's going to be another way we can define what kind of ring it is by analyzing the kind of polynomial you happen to have with the p of x. And that's going to be section 5.3. So, well, I'll see you guys on the next video, but like I said, but first we'll be taking our test number 2, and then we'll pick this thing up right after our test.